So as you said, I'm Jason Fries. I'm a postdoctoral fellow. I actually work in the Mobilize Center in addition to Chris's lab, and that's an NIH-funded BD2K. It's Big Data to Knowledge Center for leveraging big data to develop a better understanding of human health. And before, all of this work that I will mention is enabled and assisted by my great collaborators, including Sen and Alex, who we've heard with today, and then advised, of course, by Chris, and then Scott Delp in the Mobilize Center. So just to give a brief outline of how this talk is going to proceed, I'm going to start big picture to talk about motivation of why weak supervision is absolutely critical for understanding human health. And I'll talk more specifically about this idea of what I call resource regimes, or the sort of intuitive notion that different domains have very different structured resources available that you can leverage when building these systems practically. And then we'll go into some experimental results with data programming, where we talk about actually tagging biomedical named entities in PubMed documents, but doing so without any labeled data, just leveraging what's been enabled by data programming and Snorkel. So as I said, understanding human health really requires reasoning over unstructured data from a lot of different domains. So if we just consider text, we might have something like the scientific literature, and we might want to look at it in the context of the electronic health record, as Allison talked about at length earlier today. We might be interested in enabling more advanced clinical decision support systems. We might be interested in enabling interesting and innovative literature-based discovery, as such the stuff that Emily talked about with drug repurposing. And we'd like to be able to maybe think and reason over these domains and maybe think about how an EMR could be cohabitate some space with PubMed directly so that in the clinic, people could see both resources and use them to maximum extent to enable patient care. We could think about the electronic health record as living in this broader idea of how behavior and health are linked together, and all the interesting ways that we can conduct surveillance on Twitter or surveillance in social media writ large, where we can monitor risky health behaviors, or perhaps frontline surveillance for medications and things that have been classically difficult to sort of monitor in the existing infrastructure of health systems today. And what we have really, and we can think about just continuing ratcheting up our scale, where we might want to incorporate biosurveillance and think about the spread of human disease in plants and animals and humans, and how this all interplays together to give an understanding of human health in the modern era. And what we need more than anything is a dire need to be able to reason and train machine learning systems that can live in all of these spaces, and we need to be able to do it quickly and at unprecedented scales. And so what I'm going to talk a little bit about is the idea is all those little examples I gave have sort of different base level resources that are available to you that if you were to walk into a problem would be at the ready that you could start using to build a machine learning system. And I'd call these resource regimes or levels. It's really just this intuitive idea that these exist on some linear scale. But if you have a low resource regime, you will have to invest more time to get a high performance system versus something like a high resource regime where you have a lot of labeled data perhaps, and it's more quick to spin up a state-of-the-art or high performing system. To make this a little more concrete, if we took at the low resource regime, you might have very little available to you in the form of structured information. You may have a lot of domain knowledge or reasonable heuristics that you can use to inform that system, but structured data is not collected or built for these tasks. These might be things like online health surveillance. They might be things like Chris's work in human trafficking detection. It might be things that just don't have the terminology resources built as we do in other domains. If we look at something like the medium regime, which of course would include everything available to you in the low regime, this is more common for most tasks, especially in biomedicine. We have vast arrays of curated ontologies, lexicons, knowledge bases, and they are the effort of untold human hours to collect and curate. And they often contain interesting things that perhaps people haven't directly built machine learning systems to address. This could be things like medical devices that Allison discussed earlier. It could be things like bacterial subspecies or sort of niche, interesting biomedical areas to which we have a lot of structured data, but there's never been really built a system that can deal with this type of specific task. And when you really think about it, if you look at something like Bioportal, which is probably the largest biomedical ontology collection, something like 517 ontologies, 7.8 million individual classes, there is never going to be enough labeled training data for the specific ontology that perhaps best suits your task. So we really need some way to be able to repurpose things that are available to us at a quick enough speed to make them practical. And if we expand this to think about the space of relationships that perhaps exist on top of these entities, the amount of time becomes largely intractable to create hand-labeled systems for. And then we get into our high resource regime, which is what we classically think of as traditional supervised learning. But this is in fact probably the rarest regime. It is very expensive to construct these data sets, as has been indicated by people in this talk. And it's usually reserved for these very high impact areas like extracting gene names or diseases and chemicals. And it really is, again, the rarest of available things to you in things like the biomedical space. So what we really desperately want to do with this idea of weak supervision is that the medium case is so prevalent and so common, we want to be able to push that to be much, much closer to the high case, where we get rid of this idea that you need labeled data to be able to build a performance system, which is where we get into the idea of data programming and Snorkel, as has been discussed at length today. And the real advantage of Snorkel is that it sort of unifies and denoises all of these disparate structured resources and can do it in a sort of simplified and principled manner. So what I'll specifically motivate the rest of the talk with is these experiments we've done extracting biomedical named entities from PubMed text. This would include things like chemical names and disease names. This is commonly called named entity recognition. This is commonly done by using a bunch of labeled data and training something called conditional random fields or any other sequence labeling machine learning tool. We would like to do the same task, but without using any labeled data. We want to do it with data programming, only leveraging the types of structured resources and domain heuristics I talked about a few moments ago. And I'd like to specifically leverage this thing called the Unified Medical Language System, which is this gigantic human digital artifact that has been built over the course of 30 years. It includes something in the order of 1 million biomedical concepts, 100 million or 100 plus controlled vocabularies. And it's really this type of artifact that we should be able to do a much better job about leveraging and using automatically to generate these sort of critical tasks like labeling entities, biomedical entities in text. And so what this gets to is this idea that structured resources, really any ontology or anything to which you know the structure of, can be automatically turned into a labeling function. So this is just a small subset of informative attributes from the UMLS, things like pairs of relations that an entity may participate in, its semantic type, this could be like a disease or a sign or a symptom, medical device name, chemical name, antibody, et cetera, et cetera. It might be even really microscopic things like the type of term it is. Is it an abbreviation? Is it an obsolete term? It could be one of many different ontologies. These are all attributes that a human supervised over the course of untold hours and years. They are something that we should absolutely be able to leverage in a sort of automatic fashion. And again, these are just some of the subsets of things available from just one ontology or one collection of ontologies. And the advantage of data programming is that it does provide just that, this principled way to transform all of these into labeling functions. And then upon this, we can be somewhat agnostic to their inherent noise and sort of how ill-suited they might be to a specific task. And we can actually learn that by pouring these structured resources into a labeling function form. And just to show sort of toy examples of what these might look like, These could simply just be functions that check, as Alex said, dictionary membership against known ontologies or some hierarchy to label disease names in this case. And it's not mutually exclusive from sort of the simple stuff like syntactic patterns you might want to manually curate. But the point is, all of the stuff that is an ontology, like membership in dictionaries and all that sort of rote stuff, that can be completely automated. We can just generate functions using functions that produce labeling functions, factories or generators, to automatically create thousands of functions that encode this domain knowledge automatically. And what it does is it gives you sort of a programming stack of how you sort of approach the task of labeling in a data set. So for this would be a UMLS stack. You should be able to walk into a common biomedical problem, and this should be the floor upon which you start building your actual specific application. And the idea is this will make it just much faster. We can actually motivate this with numbers. If we were to take a common benchmark disease data set and look at what a supervised CRF would give you, if I took labeled data and trained a model on it, it'd give you about an F1 of 81.5. That's just the harmonic mean of precision and recall. If we were to take the most naive approach humanly possible, where we just do dictionary matching, we get maybe about a 60. If we just take the UMLS and just blast all of the information we have on semantic type and the source of the ontology, more or less push button, just denoising these labeling functions, we can get around a 74. And if you actually go in and then start layering on sort of customized domain knowledge and tweaked functions, you can get about a 79.5, which is very close to the score you would get if you use the labeled data directly. And if you just look down the breakdown, we're at about 77% dictionaries and about 18% very specific customized rules, and then some other things layered on top. And you can actually look in some of these other data sets, and we do approach sort of the scores you'd approach in a supervised learning context. And this is work in progress, so we're still iterating on getting these sort of numbers up more, and that points the way looking forward. What would we hope to see in a system that can really take advantage of weak supervision? Well, we would like to be able to enrich the scientific commons. There's something in the order of 27 million English scientific publications available online. We should be able to parse and generate artifacts of entities and relations that live within this space automatically and be publicly available for other scientists. And that type of ambitious goal is made possible by an information extraction system that can sort of better leverage weaker sources of supervision. And looking forward, as Alex hinted at, another big goal is to sort of make this simpler to use. And we would, the sort of common pipeline in these weak supervision approaches is to enumerate some set of candidates using matchers, which were basically labeling functions. And we would like to really cut that candidate extraction part out and really have the sole input semantics be labeling functions without sort of this two-step process that we sort of currently have in place. And just to wrap it up, the real hope here is that data programming pushes us further in the ability to sort of get that medium resource regime, our ability to navigate and interact with ontologies closer to something what we'd hope would be in a labeled data case. And with that, thank you.
It's okay if you want to.